Hi, welcome back to the statics review sessions. In this session, you will learn about a moment of inertia of a cross-section, which also includes how to find the centroidal axis of a composite sections, because we have then to find a moment of inertia of a cross-section about its own centroidal axis. Moment of inertia is a cross-sectional property, has nothing to do with the type of material. Is one of the factors that represent how the cross-section would resist rotation. This is what is moment of inertia is. In further design classes, you'll learn about other factors that relates to the material, but for now, we just learn about how to find a moment of inertia of a cross section, which is again it's just a property of or cross-sectional property. Most of the cross-section are composed of common shapes like rectangles or circles or triangles. The moment of inertia of a whole cross section of a composite shape would be the moment of inertia of, for example, this rectangle about its own centroidal axis, and then relate this to the whole cross section centroidal axis with something called the parallel axis theorem. The parallel axis theorem is how to relate a moment of inertia of a differential element like this here, um, based on its cross-section centroidal axis, and how to relate it to this axis, for example. So first, you always find the moment of inertia about its own centroidal axis, and then after that, relate it with the parallel axis theorem, which is the area and then multiplied by the dy, which is how far is that axis located from that axis you want to find a moment of inertia about. You notice here, this is the moment of inertia. This is also another term for the moment of inertia. Is known as the second moment of an area. So it's just a moment of an area times a distance, and then multiplied again by another the same distance. That's why we call it the second moment of an area. We'll see this in this example. This example is to find the moment of inertia of this cross section about its own centroidal axis. To do that, we need first to find where is the location of these two centroidal axes, the x and the y primes. The first step to find the location of a cross-section centroidal axis is to set the reference axis x and y, where you then can find the location of the y-axis represented by x prime, and the location of the x-axis represented by this y prime. Following is to divide this shape into common shapes, where you would know automatically where the centroidal axis is. So I could divide it into a triangle, where I know that it is just a third and two-third the location of that, and then a rectangle and rectangle. Or I can simply divide it into one big shape, which is this big rectangle, where I know the location of its centroidal axis exactly in the middle, here 120 and 150, and then subtract from that this triangle, where you will find can subtract the triangle, and you also would know the location of its centroidal axis. Um, the steps works by applying these equation. Finding the x is simply divide the moment of areas about multiplied by the x distance from its y-axis in that case, and then divide it by sum of all areas. This is very similar in finding the location of a resultant force in a system, where you can find the moment of a resultant force, and then which is equal to all the moments caused by all forces, and therefore I can divide moment of all forces and divide it by sum of the forces. It gets you the location of that resultant force. This is the same concept. So in that case, where you work with a moment of an area, you can work with moment of volumes if you need to find the center of gravity, or a moment of length, or moment of weights. But here, because it's just a 2D section, we work with moment of areas. So we start working with the equation to find that location x. The first step is here you have the area multiplied by the horizontal distance from the reference axis y to its own centroidal axis. So the area is 300 times 20, 1 times 240. So you have the 240 and the 300, and then multiply it by this distance of its y-axis from the reference axis, uh, which is a 120. We subtract from that, we said that triangle. So it's the area of a triangle if half 150 times 120, and then multiply it by the distance from the vertical distance from its own x-axis to the reference x-axis, which is, you have, if this is 2/3, this you get it from the book, that the centroidal axis is 1/3 and 2/3. So 2/3 of the 150 is 100, and then add to that is the in this example, uh, we will have to find a moment of inertia about of this cross section about this its own centroidal axis. So the first step, we need to find first where is the location of the x and y axis of the whole cross section. To find that, we have first to set a reference axis, x and y, and then find that distance, the x prime and the and the y prime. And this is you can set the reference axis wherever you want. Like anyone can set it at any location, but that's the first step. So you can set it at this corner or at that corner or even in the middle. But I'm setting it at this corner to avoid working with negative. So all the distances are measured in a positive direction. Following is to divide this cross section into the common shapes where you know for certain where the location of its centroidal axis. So you can divide it into this triangle and rectangle and another rectangle, or you can simply just divide it into this big rectangle where you know the location of its centroidal axis exactly in the middle, 150 and 120, and then subtract from that triangle where you also know the location of its centroidal axis, 1/3, 2/3 of that distance, or this distance. This you can get also from the any textbook in tables in statics or mechanics materials. The following is to apply these two equations. So it's to find the distance x, then you have to divide sum of the moment of the areas divided by sum of the areas. This is very similar to how to find the location of resultant force. So you get as the moment of the resultant force equals sum of moments of all forces in the system, which means that I can, to find the location of the resultant in a system, I just divide sum of all moments of the forces and then divide it by sum of the forces. This is works exactly the same to find the x and the y. For the centroid and center of gravity, you can use the areas, you can use the length, you can use the weights, you can use volumes. But here we will work with moment of inertia of the area, then we have to work with moments of areas. So first step is to find that location of the y-axis, which means that I will use moment of an area about the y-axis, which means that I have to multiply it by these distances, the x distance from these two shapes. We start by the area, the first shape area. This is the 300 times the 240, and then multiply it by the distance, the horizontal distance between the reference axis and its own centroidal axis, y-axis, which is the 120. We subtract from that the half height times base, which is the area of this triangle, half 150 times 120, and then multiply it by 1/3, which is that distance, the horizontal distance between its own centroidal axis and the reference y-axis. And then divide it by sum of the areas, so it's the 300 by 40 by 240, and then subtract from that triangle area. This will give us the location of the y-axis, the whole cross-section y-axis represented by this x prime. Followed is finding the location of the x-axis by finding that y prime. So it is exactly the same, but now we will have to multiply or find the distance between the vertical distance from its own x-axis and the reference axis. So here is again the area 300 times 240, and then multiplied by the vertical distance, the 150, which is measured from the x to the its own x-axis, and then subtract from that the area of this triangle, and half 150 times 120, and then multiply it by that distance, which is this area measured from the reference axis and its own x-axis. In that case, because this is located at 2/3 and 1/3, 2/3 is 150 is 100, and then add to that the 100 is 250, and then you get divided by the areas. You subtract again the area. This is exactly the same as here, and this is the location of the whole cross section x-axis located at 135.7 from the reference x-axis. So followed is to find the moment of inertia of the whole cross section. To find the moment of inertia of the whole cross section, we'll use the same divide that we did into a big cross section, and then subtract from that the moment of inertia of the smaller cross section for both axes. So if we need to find the moment of inertia about this x-axis, then we find the moment of inertia of the whole cross section of one, and then subtract from that ix2, and for the y is I y, then the iy1 minus iy2. So we subtract, we just follow, and then we keep the same reference axis because we know the location of that. So the moment of inertia is calculated now here, as you've seen in a few slides before. You have to use the parallel axis theorem. You have to find the moment of inertia of the whole cross section about its own centroidal axis, and then relate it to the whole cross section centroidal axis, which is that xy, which we know now the location of. To do this, the first part is about its own centroidal axis. You will find in most of the book, in the tables, you will find it shows the moment of inertia of a rectangle or a triangle written next to it, and it says, for example, to find a moment of inertia about the ix, then it has to be 1/12 bh cube. I give a tip to my students because sometimes the segment that you divide it to would be set compared to the whole cross section in a way that will make you don't know or get confused which side to cube. So the best way to learn that is try always to cube the side that is perpendicular on the axis you're taking a moment of inertia about. So if I need to find a ix, then I cube the h. If I need to find iy, then I cube the b. And this is the same key. So this part, we say it's I take the moment of inertia about its own centroidal x-axis, which is in that case here ix1. So I have to cube the side perpendicular to it. So that's why here it's a 112 and then 240 times the 300. And then the parallel axis theorem, trying to relate the moment of inertia I of the cross section related to the whole cross section x-axis. Parallel axis theorem here is the area of the whole section and then multiply it by the vertical distance between its own axis. And remember, this is the y that we found. So we can simply just use the reference axis and say it's just simply 150 minus the 135.7, which is that distance here, and then squared. This will give you the moment of inertia for the I x1, and then get the moment of inertia of the ix2, which is this part that I need to subtract. So again, from the table you get about its own axis. It works the same concept. You need to get about the x-axis, then you cube the side perpendicular to it, and it's 136. So 136, and for this, because I'm taking a moment of inertia about the x-axis, then I have to cube the 150. So you have a 150 times 120 times 150 cube. And then parallel axis theorem for this triangle. Notice here there's no negative sign. That you will subtract the whole cross section. So the only negative sign that you see is whether you subtract or add the moment of inertia. There's no in that system here. You have also to add which is how to relate the moment of inertia of this triangle about its own centroidal axis and relate it to this axis. So in that case, then I can just subtract the distance and also use this reference axis. So it's the area, the same area, half 150 times 120, and then multiply it by the difference between this 250 and the location. So I'm multiplying it by that distance, that vertical distance, and squared. This will give us the moment of inertia about the x-axis, which will actually let us find the first answering the first question. Moment of inertia about the x-axis, Ix, is 426 times 10 to the 6 millimeter to the 4. The following is finding a moment of inertia about the y-axis. So then we have to use the horizontal distances. So again, this is the same concept here. You see the difference between about the y-axis. Now we cube the other side that is perpendicular to the y-axis. So in that case, in a rectangular shape, we have to cube the 240 multiplied by the 300, and then this is the area times the distance between its own centroidal y-axis and the y-axis of the whole cross section, which we're talking about this small distance. To do that, I could use also the reference axis. So we have the 131 that we found, and then subtract from that the 120, and then we square that. Followed, this is the this will give you I y1, and then I y prime 2 is subtracting, that has to be subtracted from the moment of inertia of the whole cross section. So you have the 136. We use again cubing the side perpendicular, and here compare between these two, and then you just cube the opposite, in that case here about the y-axis. Then we have to cube this side, the 120 cube, and then multiply the 150, and this is a 136. This comes from the table that you grab, and then add to that the area, half 150 times 120, multiplied by the horizontal distance between its own centroidal axis and this axis. In that case would be the 131, which is that distance minus the 40. Notice here that I used always the answer here would be positive. So even if you just subtract this and it is a negative, but when you square it, it will be positive. So I just ordered it this way, which will give you positive answer too. This will give you y prime 2, and then which will also result in the final moment of inertia about the y-axis, its own centroidal axis y. It's 273 to the power of times 10 to the power of 6 millimeter to the 4. These are the steps of how to find the moment of inertia. So always, if it's symmetrical, if this was just a symmetrical system, then it would have been easier because you would know right away the centroidal axis. But I brought a section that is not non-symmetrical, so also to learn how to find the location of the centroidal axis, and then also find the moment of inertia, and also use that you can subtract one shape from the other to get the final answer, what is the moment of inertia. Final important notes that you have to pay very good attention to is when you work with finding a moment of inertia, please pay attention to first about its own centroidal axis, which side to cube. This is where many mistakes happen. Many switch the cube here to find ix, for example, and also here where it comes a lot of mistakes, finding that distance d. Again, if you need to find a moment of inertia about the x-axis, then you find the vertical distance between its own centroidal axis and the whole system centroidal axis, dy. Some would use this up here, which is not correct, because they think that you work with the x, then you have to subtract the x. Also, another common mistake, some would forget that square. Not to mention that some also would forget this section. This section sometimes doesn't exist if the whole cross section is axis just lies in the same cross section, so which means that in that case d would be a 0. So please pay attention to these points, important points, and thank you. This wraps up that session about moment of inertia, and wraps up also all sessions about the statics. Thank you and good luck.